All right, so chapter 9 is talking about hypothesis tests for means and proportions. So starting off, like everything else, we have some definitions. 9.1, our H sub 0 is what's called our null hypothesis. And it says this claim or a statement, sorry for the typo, a claim or a statement about a population parameter that is assumed to be true until it is declared false. It is assumed to be true until it's declared false, just like you're assumed to be innocent until proven guilty. So same concept we're going on here. And I'm going to kind of use that again, so I'm going to put that in parentheses here. Innocent until proven guilty. Our alternative hypothesis, which is H sub 1, is a claim about a population parameter that will be declared true if this null hypothesis is false. All right, so rejecting the null hypothesis, rejecting this innocent until proven guilty statement, rejecting the null hypothesis is false, thus declaring the alternative hypothesis to be true. Our rejection region is the region where the null hypothesis is rejected. Our critical points are one or two values that divide the whole region under the sampling distribution of a sample statistic into rejection and non-rejection region. Our type 1 error, which is our alpha error, that occurs when a null hypothesis, the true null hypothesis is rejected. A true null hypothesis is rejected. So that means this would be like an innocent person goes to jail. So the null hypothesis, the null guess that we had was actually true, but we said it wasn't true. So we made an error there. So our significance level, alpha, is the probability of making a type 1 error. So it's the probability that our null hypothesis is rejected given that our null hypothesis is true. So going back to test 2. And then our type 2 error, which this is the letter beta. Oh, I put it right there, beta. Greek letter. Type 2 error, a beta error, an error which occurs when a false null hypothesis is not rejected. So it was false, but we said it was true. So those are two vice versa errors. So our probability, our beta is our probability that our null hypothesis is not rejected given our null hypothesis is false. So this would be like they're guilty, but they go free.
Yeah.
You're making me nervous laughing over there. Guilty but goes free. Yes, hopefully we don't make that error. Hopefully we don't make either error in real life. Hopefully it's kind of bad either way. But
Guys like that in video games that usually throw off a building.
oh, great. Well, I'm glad that you're having some justice, I guess. I don't really know. So beta is the probability of making a type 2 error. The power of the test is 1 minus beta, which is probability of not making a type 2 error. All right, so let's kind of start looking at some of this. So there's 3 possibilities for a test. We could have a 2-tail test, which in fact is where our rejection region is in both tails. So this is very visual. We're going to draw graphs, and like we've been doing this whole time, to see whether we reject it or not. So it's very visual. So for this, whenever we have our null hypothesis, it's going to be equals. And then our null hypothesis means it does not equal. So we have our critical values. So we're going to call this C1, and then we have our C2 over here. These are our rejection regions. Remember, if this whole thing is alpha, this is going to be alpha split in half, so alpha over 2 for each one. This is in the middle, our non-rejection region. Which in the middle is wherever we fail. We do not to reject, we fail to reject the null, so H sub 0. And then this is the rejection region. So if our answer here lies in the white part, then we failed to reject it. If it ends in the rejection region, then we reject it. So that's a two-tailed test. We also have a left-tailed test. For our left-tailed test, it's going to be our null hypothesis is going to be equals or greater than or equal to. And then the null hypothesis is going to be the opposite, so it's going to be less than. And for this case, our rejection region is in the left tail. So we have our critical value in the left tail. We only have one tail, so this is going to be our alpha. So this is going to be our non-rejection region. And then last but not least is the right-tailed. So the rejection region is in the right tail. In this case, our null hypothesis either equals to or is going to be less than or equal to. Our null hypothesis is going to be greater than. So in this case, our critical value is on the right side, so that will give us that right tail test. There's only one tail, so this whole thing is going to be alpha. And then the non-shaded region is our non-rejection region. So for this case, for all of these cases, you always, to tell what kind of tail it is, if it's left tail, right tail, or two-tailed, we're always going to look at the null hypothesis. I'm sorry, at the alternative hypothesis. H sub 1, which is the alternative. To determine the type of test. So for example, two-tailed test, it's going to be not equals to. Left tail's test, it's going to be pointing to the left, so it's going to be less than. On the right tail test, it's pointing to the right, so it's going to be a right tail. So always use the alternative hypothesis. Don't look at the null hypothesis. Yeah, sorry.
X or U.
Which one?
On your curve.
Alpha.
That's alpha.
Yeah, it's this thing up here.
Okay, good.
Sorry. Yeah, kind of. Yeah.
It's supposed to look like.
Yeah, it's supposed to look like it's a Greek A.
Still looks like me.
Yeah. It looks like, I don't know. Yeah, I feel like it looks different every time I draw. This is what it's supposed to look like. That's whenever you type it, it's supposed to look like that. But anyways, thank you for asking me a question. Any other questions on page 1? before we go to page 2. So again, this is, don't freak out too much yet because we're kind of just going through definitions. We're going to use it, and that whenever you kind of use it is what helps me, so hopefully that'll help you too. You ready for the next page?
So you're going to translate now.
Yeah. Well, not yet, but yeah. So, sorry. 9.2 is hypothesis test for our mean when our sigma is known. So whenever we use a normal distribution, and our table is when n times p, we talked about this earlier, is greater than 5, or n times q is greater than 5, due to the central limit theorem. And then we want to talk about our errors again. We kind of talked about it before. Let's talk about it again. So our possible hypothesis test outcomes. So the actual situation, our decision says that we did not reject the null. I forgot the little 0 here. So we did not reject it. So we said that it's true. The wording is super weird. I wish I had said like true or false, but the wording is we rejected it, which we're going to, rejected means we're going to say it's false. Or we are going to not reject it, which means we're going to say that it's true. It's just the wording that statistics uses. So if our null hypothesis is true, and we say it's true, we do not reject it, we're good. Correct decisions made. No error. But if we say it's false, but it's true, we're letting an innocent person go out of jail, this is going to be a type 1 error. And that's a Roman numeral, thank you. Or an alpha error.
Sounds like a misdemeanor. I'm just kidding.
That's funny. A type 1 error. All right, so likewise, what if the person was guilty? What if the null hypothesis is false? But we said it's true. So they're guilty, but we're saying that they're getting out free. Type 2 error. Or this is what was called the beta error. Again, capital B Greek letter, so that's why it has like that funny tail and it's kind of like italicized kind of. But if we say it's false and it is false, we're good. We made the correct decision.
Now, is there some sort of like, if we say, let's say we did the type 2 error or the type 1, we have to do like some sort of equation to get it.
Oh no, you're good.
No.
It was just kind of more like definition wise for this class. In the future, yes, but just for this class, it's kind of more just definition wise. Great question though. Anything else? So let's keep going for time's sake. So our level of significance is our alpha, which we talked about before. So let's kind of like still take what we talked about on the previous page and kind of add to it. So if the null hypothesis, if they tell us it's equal and the alternative hypothesis is not equal, that's going to be a two-tail test, where we're going to have two tails. And because we have two tails, the whole thing is alpha. The shaded region is alpha. So we have to break it up into alpha over 2. And in the middle is our non-rejection region. The rejection region is what's shaded. That's where we say it's rejected if it's in the shaded region, and it's not rejected if it's in the not shaded region, in the white region. All right, so here, if we have a right tail test, they give us a right tail test. So if it's right-tailed, then we know the alternative hypothesis has to be pointing to the right. It has to be greater than, because they give us the picture of the right-tailed test. So that means, going on from the previous page, our null hypothesis is probably less than or equal to, or it could be equal to. Sometimes they kind of throw that in there as well. Last but not least, if we are given a left-tailed test, that means our alternative hypothesis is going to be pointing to the left, so it's going to be less than. And our null hypothesis is going to be greater than or equal to. And these little stars represent our critical values that we found before, our critical values. So it's kind of like putting everything together. Last but not least, a couple little notes. Our critical value approach uses the rejection points. Our p-value, our probability value approach, there's two different ways of doing this. We're going to do it both ways so you can figure which way you like better yourself. Uses the likelihood of occurrence of a given event, and it determines the significance of your result compared to alpha. So let's do an example. Before we go to the example, questions, comments, concerns thus far. So I know we're low on time. If you need to go, you're welcome to go, but I have to stay and finish. We have to get some of this done. So next page. A random sample of 120 observations produced a mean of 29. The critical value and the observed value of z for the following test of hypothesis using alpha of 0.01. The population standard deviation is known to be 9, and the population distribution is normal. Okay, so let's kind of think about what all they gave us over here. They told us our sample size, Rn, is 120. They told us our sample mean, which is x bar, is 29. Find the critical values observed for of z for the following hypothesis test using our alpha is 0.01. They tell us the population standard deviation, so our population standard deviation is known, and it's going to be 9. They give us the null hypothesis is that our mu equals 28 versus our alternative hypothesis. We see that it's not equal, so boom, that tells us it's going to be a two-tailed test. Round your answer to 2 decimal places. Okay, great. All right, so we know it's going to be a two-tailed test. In the middle is our non-rejection region. On the outsides are our rejection regions. We know on each side is alpha over 2. So 0.01 over 2, which is 0.005 on both sides. It's symmetric because they told us it was, our population distribution is normal. So going old school, we need to find our critical values. We need to find our z-scores. In our calculator, remember we did the inverse norm? Our area to the left was 0.005. Area to the left right here. Once we find one, we can find the other one because it's symmetrical. It is normal, so our mean is 0. And our standard deviation is 1. We're looking for z. So second bars, second bars, go down to inverse norm. I'll write that on here in case we forgot. Second bars. And our inverse norm, area to the right is 0.005. I'm sorry, area to the left is 0.005. Mean is 0, standard deviation is 1. boom, we get negative 2.575, which will round up to negative 2.58. So we know this left side is negative 2.58, so this right side is positive, positive 2.58. So this is our Z critical left. Our Z critical right is just the positive version, so positive 2.58. So boom, that's this answer. Our right one is 2.58. Our left one is negative 2.58. Now, so we have our table. This is what we're going to use. This is our critical value approach. This is what we're going to use. But we need to find, okay, what is actually observed? So that way our observed one is to see, okay, where does it at? If it's in our shaded region, we're going to reject the norm. If it's in the white region, we're going to fail to reject it. So let's find our observed value. We first have to find our sampling standard deviation, which is, sorry, thank you. All right, so now to find our observed value, you have to first find our sampling standard deviation, which is our standard deviation over the square root of n. Our standard deviation, they told us, was 9 over the square root of 120. 9 divided by the square root of 120. 0.8215838 is going to round up to 4. I just kind of remember went out enough so that way rounding won't mess me up. So our z observed is going to be our x bar minus our mu all over our sampling standard deviation. Is it coming back? Slowly. Our x bar, they told us, is 29. Our mu is from our hypothesis test, so we know it's 28. All over that sampling standard deviation, so 0.821584. So plugging that into your calculator, make sure whenever you plug this into your calculator, you put the top in parentheses, so that way it's grouping it together, or you can say 29 minus 28 is just 1. Either way you want to do it. Is it just me, or like sometimes whenever you do this stuff, I like am so nervous. I'm like, I don't know, what if 29 minus 28 is not 1 this time? Let me plug it in just in case. Like, you know, like I don't know, I just don't trust myself, I guess, but I should be more or less likely to trust myself whenever I have to like plug it in. Anyways, oops. There's our answer. It said round to 2 decimal places, so 1.217 is going to round to 1.22. So that is our z observed. So going to, I want to try to put both things so that way we're still copying. So going to our thing that we made. This is what's important. So finding our z observed. If in the middle, remember a 0. 1.22 is somewhere like right here. Z observed, which is 1.22. So because it's in the white region, it's in the non-rejection region, it's in the non-shaded region, we are going to fail, this is our answer, fail to reject the null hypothesis We're going to say it's true. We're going to fail to reject. It's like a double negative. And I want to put in here because our z observed is in the non-rejection region. So basically, it's kind of taking stuff that we've already done, putting it together, and just see where it lands on the graph. And that's it. So we're going to do another example. We have plenty of examples, don't worry. Before we go to the next page, questions, comments, concerns so far? All right, so let's try another one. Yes, good. Look at you. Right tail. Yep. So a random sample of 16 observations taken from a population produces a sample mean of 75.4. The population is normally distributed with a standard deviation of 6. Whew. Okay, because we really don't read. We kind of just, okay, read it, and then we kind of take what we want out. So I know I want that my sample size, my n value is 16. My sample mean, my x bar, is going to be 75.4. They give us our population standard deviation. Notice it's known. They say the population is normally distributed with the standard deviation. So we're talking about the population here. So that's why we're still able to use z values, because we know our population standard deviation, and we know it's going to be 6. Our alternative hypothesis says greater than. It's pointing to the right, so we know we're going to have a right tail test. And it asks us to calculate the p-value. Remember, the p-value is the area of our shaded region. So first we need to find our sampling standard deviation, which is our population standard deviation over the square root of n. So 6 over the square root of 16. Oops. Which is 1.5. We need to find our z value so that way we can find the area under the curve. So z observed is our x bar minus our mu all over our sampling standard deviation. Our x bar in this case is 75.4 minus our mu, which they gave us here, is 72. All over our sampling standard deviation we just found was 1.5. Again, whenever you put this into your calculator, it's a fraction, so make sure you put the top in parentheses. And Larry, you good? I was just checking on you. So we get 2.266, which will round up to 2.27. So just like we did before, we need to find the area under the curve. So in our calculator, we're going to do the normal CDF. By the way, let's kind of do our pictures. So in the middle, we have 0. Here is our z value, which is 2.27. And it's right-tailed, so we know it's going to be the area to the right. So this will help us see our lower bound and our upper bound. Our lower boundary is 2.27. Our upper boundary is going to infinity. So 1e to the 99th. Comma 0, comma 1. So second bars, normal CDF, our lower limit's 2.27, our upper limit's infinity, 0, comma 1, and we get 0.0116. So we know this area is 0.0116, and that's our p-value. That is our area of the shaded region. So if the significance level is 0.01, would you reject the null hypothesis? So we want to take our alpha, which is 0.01, and we want to compare it to our p-value, which we just found is 0.0116. So it's saying sorry, I was thinking, okay, so if this value is 0.0166 and we have 0.01, that's less than this. So this shaded region would be smaller. So it would be if we were to like graph it, our alpha level would be less than this. So alpha would be like somewhere over here, which is 0.01. So it's in that rejection region. trying to think how to explain this better. So our alpha, which is 0.01, and our p-value, which is 0.0116. Our p-value is bigger. That's what we're really looking at. We're really not looking at the graph here. So, because our p-value is bigger, and I'll explain this in 1 second, we are going to fail to reject the null hypothesis. That is our answer.
So you don't worry about the shaded area.
This is okay. So the first version we talked about doing, going back a couple pages. We talked about two different approaches. We did the critical value approach, which is what we just did, and then we talked about the p-value approach, which is what this is. So these are the two approaches that we're going to look at. So what this is saying is, I'm trying to think of like the best way to explain it, like in not mathematical terms. We're going to fail to reject it because our alpha, if we were here, this would be like our new shaded region, is smaller than our rejection region. So we don't like have enough evidence. Maybe going back, maybe I'm watching too much Dateline, but going back, we don't have enough evidence to prove that they're guilty, right? So even though we think that they're guilty, we don't have enough evidence to show it. Does that kind of make sense? So here we don't have enough evidence to say that our p-value is enough. So that's why we would fail to reject it. We don't have enough to overwhelm the rejection region. So that's why we would fail to reject it. Versus, what if our significance level, what if our alpha is 0.025 compared to our p-value, which is 0.0116. So our alpha, which is 0.025, and our p, which is 0.0116. Our alpha this time is greater than or equals to. These are like our two, this is our p-value approach, our two options here. So because our alpha is greater than or equal to, so we have enough evidence to reject the null hypothesis, because this time it would be overwhelming our shaded region. So mainly the graph is all we're doing with the graph is to find our lower and our upper bounds. That's really all we're looking at for our graph for this one. And this is because our alpha is larger than our rejection region. It is overwhelming our rejection region. So maybe this is confusing. So we're going to do another example. Before we do that next example, questions, comments, concerns for me? So a random sample of 118 observations produce a sample mean of 33. Find the critical and observed values of Z for the following. Test of hypothesis using alpha is 0.05. The population standard deviation is known to be 9, and the population distribution is normal. So a couple of things. Let's talk about what we know. So N we know is 118. Our sample mean, our X bar, is 33. We know our alpha is 0.05. The population standard deviation, so we know that is going to be 9. Our null hypothesis is that our mu equals 28, and our alternative hypothesis is that it is greater, our mu is greater than 28, so we know it's going to be a right-tailed. So we know if this is 0, over here is going to be our right tail. So first, let's find our critical value. Go into our calculator or inverse norm. We're trying to find that z-value. We need to put in the area to the left. We know this is alpha, which is 0.05. So our area to the left, because most of us have a calculator that we have to put in the area to the left, is 1 minus alpha, so 1 minus 0.05, which is 0.95. Comma 0, comma 1. So second bars. Second bars. Inverse norm. Area to the left is 0.95, 0, comma 1. Area to the left, so that way we're all doing the same thing. If you have the calculator like mine, or we have the option, you can put in 0.05 and say area to the right. So that's okay too. I'm just trying to make it fair for everyone. And we get 1.644, which will make that critical value 1.64. So our z critical left is 1.64. So now we need to find our z observed. To do that, we first need to find, remember our z observed. Oh, let me just put equals to here. X bar minus our mu all over our sampling standard deviation. So we need to find that sampling standard deviation real quick, which is our population standard deviation over the square root of n. So 9 over the square root of 118. So 9 divided by the square root of 118 gives us 0.82851. So 0.8285. Now plugging everything in, x bar is 33 minus our mu, which they gave us in our hypotheses, are 28, over that sampling standard deviation we just found was 0.8285. Make sure again that you put the top in parentheses. So we get 33 minus 28 all over 0.8285, which will give us our critical value of 6.035, which will round up to 6.04. And that's our z observed. So that means our z observed is like way over here. So it's in the shaded region, it's in the rejection region, so we are going to reject the null hypothesis. And that's our answer, reject the null hypothesis. Because our z observed is in rejection region, which is the shaded. And that's it for this example. Questions, comments, concerns thus far for me? I want to do like a couple more. Are we good with page 4? All right, so let's go to page 5. The manufacturer of auto batteries claims that the mean life of all batteries is 45 months. So we know of all batteries. So that's our mu, is 45. A consumer protection agency wants to check that this claimant took a random sample of 24 batteries. So that's, we know our N is 24. They found that the mean life for this sample is 43.40. So our sample mean, our X bar, is 43.40. Using a normal distribution with a population standard deviation. So we know our population standard deviation. And that's 4.5. Find the null hypothesis, the alternative hypothesis, and the p-value when the alternative hypothesis states that the mean life of the battery is less than 45 months. So what's telling us is it's going to be a left tail test. Would you reject the null hypothesis if the significance level was 0.25%? So this is telling us our alpha is 2.5%. Moving the decimal over twice to the left, which is 0.025. All right, so we have everything that we know. Let's kind of start taking this. So we need to find the null hypothesis and the alternative hypothesis. They tell us the alternative hypothesis is telling us that the mean is less than 45. So going back to that first page, we can say that our mean equals 45 or is greater than or equals to, either way. But that'll be our first answer. So we need to find our z observed so that we can find the p-value. Which is x bar minus our mean all over our sample standard deviation. So let's find our sample standard deviation, which is our population standard deviation over the square root of n. So 4.5 over the square root of 24. Which is 0.91855, which will be 0.9186. Now plugging everything in to find our z observed, we get 43.40 minus 45, which is our mu, all over 0.9186. Remember to put this top in parentheses because it's a fraction in our calculator. Dividing that out, we get our z observed as negative 1.741, which will be negative 1.74. So we need to find our p-value. To find the area under the curve, I want to draw my curve. I apologize for not putting one on here. So that way I can find my lower boundary and my upper boundary. So we know it's negative, so we know it's on the left-hand side. And they told us it's a left-tailed test. So we can see for our p-value that we're going to plug into our calculator our normal CDF. Our lower limit is negative infinity, so negative 1 e to the 99th. Our upper boundary is at negative 1.74. We're looking for, we have z values, so it's going to be 0 and 1. So in our calculator second bars, normal CDF, our lower limit's negative infinity, our upper limit's negative 1.74, 0 and 1. And that will give us 0.0409. And that is our p-value, so we know that's the area under the curve. So because we have a p-value, it is telling us to use the p-value approach. So we're going to use our p-value approach. So we're going to take our alpha, which is 0.025, and compare it to our p-value. Which is 0.0409. We know alpha, which is 0.025, and our p, which is 0.0409. 0.2 and 0.4, 0.4 is bigger, so our p-value is bigger. So if our p-value is bigger, we are going to fail to reject the null hypothesis. Our evidence wasn't enough, so we have to fail to reject the null hypothesis. Because alpha is smaller than the rejection region, which is our p-value. So we don't have enough evidence, so we have to fail to reject it because our alpha is smaller. So questions, comments, concerns, how could I help you with this one, please? Perfect. All right, so let's do another example. I know, stick with me a little bit. So we have a steel corporation that produces iron rods that are supposed to be 36 inches long. So that's going to be our mu. The machine that makes these rods does not produce each rod exactly to 36 inches long. The lengths of the rods are normally distributed and vary slightly. It is known, so normally distributed, so we can use our z values. So it is known that when the machine is working properly, the mean length of all rods produced on the machine is always equal to 0.035. So that is going to be our sample mean. The mean. All right, so the quality control department, the company takes a sample, so N is 20 of rods every week, and calculates the mean length of the rods, tests the null hypothesis. So it's telling us our null hypothesis is that our mean equals 36, and our alternative hypothesis, which is that our mean is not equal to 36. So boom, we know that it's a two-tailed test. If the null hypothesis is rejected, the machine is stopped and adjusted. In the recent sample of 20 rods, it produced a mean length. So our mean was going back to 36.015. That 36.315 is our standard deviation. So it's off that much, and that's going to be what's our standard deviation. So our population standard deviation is known, and that was our 0.035. So you pretty much have everything that we need to see if we're going to reject the null or not. So first, let's find z observed, which is x bar minus our mean all over our sampling standard deviation. So that means first we have to find our sampling standard deviation, which is our population standard deviation over the square root of n. So 0.035 over the square root of 20. And we get 0.0078. Let's do 26, just so that we have plenty. So our x bar we said was 36.015 minus our mu, which we said was 36, all over the sampling standard deviation. It is a fraction, so make sure to put the top of it in your calculator with parentheses. So 36.015 minus 36 divided by 0.007826, which will give us 1.916, which will round up to 92. Because it's a two-tailed test, we know we're going to have the positive version and the negative version. So in the middle we have 0. The positive version is 1.92. The negative version is negative 1.92 because we know it's a two-tailed test. So just like before, we have to find the p-value now, which is our shaded area. Which is our normal CDF. Once we find one, we can find the other one. So our finding this one first, which remember is alpha over 2. So our lower boundary is negative infinity, so negative 1 e to the 99th. Our upper boundary is negative 1.92. Our mean is 0. Our standard deviation is 1. You could have also did from 1.92 to positive infinity. It's the same thing either way. So second bars, normal CDF, negative infinity to negative 1.92. So that should all look like this in our calculator. And we get 0.0274. But this is only this half. So we have 2 of them. So that means you have to multiply by 2. So let me write a little note here. So this is only one of the shaded regions. Shaded. So we have 2 shaded regions. So multiply by 2. So our p-value is 2 times 0.274. So times 2 will give us 0.0548. 57 is going to round up to 6. I want to write one more little note. Let me get a different color. So I said we found this one. You can also find this one. So either way, we can use either shaded region or normal CDF from 1.92 to positive infinity. To find the area. But then we have to multiply by 2 to find the entire shaded area. So because we have our p-values, last but not least, we're going to use the p-value approach to see if we reject the null or not. So comparing our alpha, which says calculate the p-value for the test of hypothesis. Based on this p-value, will the quality control inspector decide to stop the machine and adjust it if he chooses the max probability of a type 1 error? So it's telling us our alpha is 0.025. So our alpha is 0.025, and our p-value we know is 0.0548. 6 if you want to say. Our p-value is bigger, so we are going to fail to reject the null. So we don't have enough evidence, so fail to reject the null hypothesis. Because our alpha is smaller than our p-value. So it says, will quality control inspector decide to stop and adjust the machine? So if we fail to reject the null, then it doesn't need to be adjusted. So the machine does not need to be adjusted. Questions, comments, concerns on this one? Let's do one more. One more. I'm sorry. Me too. You stuck it out this whole time. You only have one more to go. Thank you. All right, so page 7. For the following significance levels, what is the probability of making a type 1 error? And it tells us that our alpha value is 0.06. So it pretty much tells you the answer. Alpha is our probability of making a type 1 error. So our probability is 0.06. Done. We're going to do this next one, but that didn't really count as an example. I like that one, though. I'll take that one. Remember that type 2 was our beta. So I kind of just wanted to make sure that you understood what alpha was really saying. So our next example, it says, consider our null hypothesis is that our mu is 80 versus our alternative hypothesis is that it's not equal to 80. So we know two-tailed test just by looking at it. For a population that's normally distributed, a random sample of 25. So we know just by looking at it, our random sample n is 25. Is taken from this population, produces sample mean. So x bar is 88. And our standard deviation is 6.2. It's talking about the sample mean and a sample standard deviation. So our sample standard deviation is x is 6.2. This is our sample standard deviation. So with that being said, our population standard deviation we don't know, is unknown. Using our alpha is 0.01. Would you reject the null hypothesis? So going back to, I want my null hypothesis is that our mu is 80, and our alternative is that it's not equal to 80, so that's telling us it is a two-tailed test. So because we have S values, just like we did on chapter 8, we're going to use our T values. So let's find our T observed, which is our X bar minus our mean all over our sample standard deviation, our sampling standard deviation, which is our S over the square root of n. So 6.2 over the square root of 25, which in our calculator is 1.24. So our T observed is 88 minus our mu, which is 80, all over that 1.24. Again, make sure to put this top in parentheses. And we get our T observed is 6.4516. So this time we're going to use the critical value approach. So we need to find our critical values. So to do that, we're going to use our T table. Because we don't have Z's anymore, we have T's. And we know our area is we have a two-tailed test, so it's going to be alpha over 2 because it's two-tailed. So we have 0.01 over 2, which is 0.05, And our degrees of freedom is n minus 1, so 25 minus 1, which is 24. So going to our t table, real quick, looking at 24 and looking at 0.005, we have 2.797. So t equals 2.797. Because it is two-tailed, we also have the negative version. So looking at our graph, in the middle we have 0, we have negative 2.797, and we have positive 2.797 as our critical values. So this would be our critical right and our critical left. My pictures are so beautiful. Remember, this is going to be alpha over 2, which is 0.01 over 2, which is 0. Oops, I forgot a 0 here, I'm sorry. 0.005. So we found our t observed. So now we just need to see, where does our t observed lie in this? Our t observed was 6.45, which is somewhere over here. So it's in the shaded region, so it's in the rejection region, so we are going to reject the null. The question was, would you reject the null? So yes, reject the null hypothesis. Because our t observed is in the rejection, which is the shaded region. Remember, in the middle is the non-rejection region. And that is our example for page 7. All right, the president of a university claims that the mean time spent partying by all the students at this university is not more than 7 hours per week. A random sample of 40 students taken from the university show that the time spent they spent on average 9.8 hours partying per week with a standard deviation of 2.3 hours. Test at the 2.5% significance level whether the president's claim is true. All right, so a couple different things. Let's start off by writing what we know. So we know n is 40. They tell us the average, so x bar, is 9.80. And they tell us the sample standard deviation is 2.3. So our population standard deviation is unknown. But we do have the sample standard deviation, which is S. So we know our S value is 2.3, our sample standard deviation. So that's telling us that we're going to use t values. What else do we know? We know our significance level is going to be 2.5%, which is 0.025 whenever we move our decimal 2 places to the left. And let's use the critical value approach. So we have our null hypothesis and our alternative hypothesis. It says that it's not more than 7 hours per week. So our null hypothesis is that our mu is not more than, is less than or equal to 7. This will tell us right here it's going to be a left tail test. And that means our null hypothesis is that our mu equals 7. I don't know why I put 0. Equals 7. All right, so let's see. What else do we need? We need our sampling standard deviation, which is our S over the square root of n. So 2.3 over the square root of 40, which we can either leave as is or we can put this into our calculator. Yes. Oh, yeah, thank you so much. So if we put it into our calculator, 2.3 divided by the square root of 40, that will give us 0.36366, which will round up to 7. We need to find our t observed. Which is x bar minus our mu all over our sampling standard deviation that we just found. Our x bar is 9.80 minus our mu, which is 7, all over our sampling standard deviation, which is 0.3637. So up top, make sure to put these in parentheses at the top of our fraction. .80 minus 7 divided by 0.3637. And that will give us our t observed is 7.699. 7.6986 will round up to 7.699. So we found our t observed. Now we need to use and find our critical values using our t-table. We know our area is our alpha, which is 0.025. We know it's a left-tailed test. And we know the area to the left is alpha, which is 0.025. We also need our degrees of freedom, which is n minus 1, which is 40 minus 1, which is 39. Sorry, thank you. So going to our t-table. Our degrees of freedom we said was 39. So looking at 39 and going over to 0.025. So our degrees of freedom column is going to be 39. Our area Yep, 2.023. Now, this says area to the right. But remember, we want the area on the left side, so we need to make it negative. So make negative. Since it is a left-tailed test. So our T critical is going to be negative 2.023. So if we know this is 0, this will be negative 2.023. And then our T critical. And then our T observed is positive 7, so somewhere way out here. 7.699. Remember, this falls under the non-shaded region, so this is the non-rejection region. So since T observed is in the non-rejection region, we are going to fail to reject the null hypothesis. Which means, meaning the president's claim is false. And that's page 8. Questions, comments, concerns on this one for me, please. For this next one, I'm going to show you, this was the critical value approach. I'm going to show you both approaches so that way we can kind of see the difference of the two. So let's go there. Page 9. A random sample of 18 observations taken from a normally distributed population produced a sample mean of 42.4 and a standard deviation of 8. Find the range of p-value and the critical and the observed values of t for each of the following tests using a significance level of 0.01. So it tells us our null hypothesis is that our mu is equal to 46, and our alternative hypothesis is that mu is not equal to 46. So this not equals automatically tells us it is going to be two-tailed. Perfect. A two-tailed test. So let's see what we know. I know n is 18. There's 18 samples that we're looking at. A sample mean, so our x bar is going to be 42.4. A sample standard deviation, so that's going to be s, is 8. So again, our population standard deviation is unknown. So that means we're going to use t-values. And what else do we know? Our significance level, our alpha, is going to be 0.01. So let's start off by finding our t observed. So for that, we need our sampling standard deviation, which is s over the square root of n. So 8 over the square root of 18. Plugging this into our calculator. .8856. Now finding our t observed, which we know is x bar minus our mu all over our sampling standard deviation. X bar is 42.4 minus our mu, which they give us is 46. All over the sampling standard deviation we just found is 1.8856. Remember, the top of our fraction needs to go in parentheses, or a lot of you I know put in the top and then press enter and then press divide. That's fine too. And we will get our t observed is 1.909. Negative 1.909. So we found our t observed. And it asks us for the range of p-values. So that range of p-values is telling us to use the p-value approach. So we need to find our range of p-values. So if we know our t observed is negative 1.909, we're trying to work backwards. So we're going to go to our t table, and because it's only positive, we're going to use positive 1.909. Since our t chart, our t table, is all positives. And our degrees of freedom is n minus 1, so 18 minus 1, which is 17. And what we're going to do is we are going to look on our t table and find the range of two areas that contain t equals 1.909. I'll give you a second to write that, and I'm going to bring it up and show you. So real quick, I'm going to show this again, but let's go to our t table. We know our degrees of freedom is 17, so let's go ahead and look right there. And we're looking for our area that goes between 1.909. So it looks like 1.909 is between these two t values. So it's between these two areas, 0.05 and 0.025. That 1.909 lies between these two numbers, between these two areas, between these two p-values. So whenever we write this, we want to write it from least to greatest because it's going like in order. So our smaller one is 0.025 is less than our p-value, is less than 0.05, which is saying our p-value lies between those two areas. But remember, This is the area to the right. But if we go back to the problem said two-tailed. So that means I have two of these areas, on the left and on the right. So that means I need to multiply by 2. So since it's going to be two-tailed, test, we're going to multiply by 2. So that means 0.025 multiplied by 2 is 0.05. And 0.05 multiplied by 2 is 0.10. So this is the range of our p-values. Our p-value lies between those two things, those two values. So we found our p-value range. So now we need to see, do I reject? All that good stuff like usual. We know that our alpha was 0.01. And we are going to compare that to our biggest or our largest p-value, which in this case was 0.10. So I can see that my alpha compared to my p-value, my alpha is 0.01, my p-value is 0.10. Our p-value is larger. So that means we're going to fail to reject the null. So fail to reject the null.
So when that happens,
Say it one more time.
so if it fails, then it just fails.
It fails to. Say it one more time.
Now, if it fails, does it fail, or do we have to actually like try to make it prove it?
Oh no, that's just the answer. That it's not.
Okay.
That it fails. You either failed to reject it. That means kind of like you're accepting it, or but that's like our answer: fail to reject or reject. And we're failing to reject because alpha is smaller than the p-value, which is the rejection region. So that's our p-value approach. We're going to do the same thing now using the critical value approach. I can write smaller. Which is using our graph. We know we have a two-tailed test. We know in each tail is going to be alpha over 2. Our alpha is 0.01. So divided by 2 will give us 0.005. In the middle we have 0. Now we found our t observed, but we don't know what these two values are, our critical values. So we need to find them. So on our t table, we know the area is going to be 0.005, and our degrees of freedom is n minus 1, so 18 minus 1, which is 17. So using that information, we can find our critical values. So going real quick. So looking at 17. Our area is 0.005. 0.005. Going down to 17, we get 2.898. 2.898. Now we have two tails, so that means this one's positive 2.898 and this one's negative oops, 2.898. So our T critical left is the negative 2.898, and T critical right is positive 2.898. So that means our T observed that we found earlier is negative 1.909. So that means it's somewhere right here. It is in the non-rejection region, so we are going to fail to reject the null. So either way, our answer was fail to reject the null, whether we did the p-value approach or the critical value approach. Since it's in the non-rejection region. It was in this white region, which is our non-rejection region. And that's example on page 9. A lot of times it asks us for all of these values. So even though we got the same answer either way, the question asks us to find the p-values and the critical values. So it asked us to do it both ways. So we had to go through both steps. So questions, comments, concerns on this one? Ready for the next one? Let's keep rolling. Page 10. What is it?
Got 8 more pages.
8 more pages? Okay, we can do it. That's what I was just looking at. Did you read my mind? All right, page 10. A random sample of 26 observations taken from a population that is normally distributed produces a sample mean of 58.5 and a standard deviation of 7.5. Find the range for the p-value and the critical value and the observed value of t for the following test if a hypothesis using alpha is 0.01. So it gives us our null hypothesis is that our mu is 55 versus our alternative is that mu is not 55. Rounding our answers to 3 decimal places. So let's kind of see what we got going on here. So, you know, just by looking at it, because it's not equals to, we know this is going to be a two-tailed test. What do we know? We know n is 26. We know our sample mean, our x bar, is 58.5. Our sample standard deviation, again, our population standard deviation is unknown. So we're going to use S and T values. So our S is 7.5. That means our S sub x bar is S over the square root of n. So 7.5 over the square root of 26. What do I got going on here? 7.5 divided by the square root of 26, which will give us 1.47087 is going to round up to 9. While we're here, let's find our t observed. We have everything that we need to find our t observed, which is x bar minus our mu all over our sampling standard deviation. So 58.5 minus our mu, which is 55, all over that 1.47087 709 that we just found. Remember to put the top of our fraction in parentheses. 58.5 minus 55 divided by 1.4709. And we get that our t observed is 2.3794, so it's going to stay 2.379. It said round t to 3 decimal places. So 2.379 is our t observed. Now let's find our p-value range. So let's do our p-value approach like we just did on the previous problem. So using our t observed, which is 2.379, and our degrees of freedom is n minus 1, so 26 minus 1, which is 25. Just like the previous problem, we're going to find the range. Of the two areas, because it's two-tailed test, that contain t. So from the table, give you a second to write that down before we get to the table. So our degrees of freedom is 25. And we are looking for our t observed, which is 2.379. So it looks like 2.379 is between these two values. So these two areas are 0.01 and 0.005. Remember, we want to write it in least to greatest. We want to write it in order.
We're looking for 25. We're on 25, right?
Oh, I'm sorry.
I'm
Thank you.
just don't know if I'm right or wrong.
We are looking for 25, yes. But 2.3 is not between 2.4 and 2.7. So I was making sure you're paying attention. Good job. 2.3 is over here. Between these two. So it should be between now 0.01 and 0.025. Are y'all on the same page? Thank you. And that's why I don't look at your phone during class. And it wasn't even a good, I was like kind of worried. It was like a Cyber Monday text. Like, I don't even know how they got my number.
Getting him all day.
Really? You guys find any good deals? I haven't done any
Yeah, I
Christmas
have.
shopping. You have?
Yeah.
Good. For yourself or for Christmas presents? Huh, Aaron? Deals for yourself? Hey. Huh?
And
Aaron, deals for yourself or for Christmas presents?
oh, I didn't know my Christmas shopping back in October.
Oh, don't even be bragging, boy. I haven't even done anything. Dang. You want to do it for me then? All right, anyways. So we said it's between 0.01, we're going to put it in order, and 0.025. Two-tailed test, so that means we're going to have two of these areas, so that means multiply by 2. Everyone's saying to get an air fryer.
What's that?
I haven't done any.
Get a ninja foodie.
What?
A ninja foodie.
A Ninja Foodie? You think that's a good one?
Mom has that. She cooks everything out of that.
Is that the pressure cooker?
It is, and it does.
It does everything.
Everything.
Yeah, it does everything.
Oh.
It's just great.
You can like cook frozen chicken in like 2 minutes or something stupid, right?
I think so. It's really good. Just try it.
Dang.
Just look at it.
Yeah. I have Instant Pot and I've used it like twice. I was so excited, but.
That's how I was. I used it once.
What? They scary? They scary? Me too. I think that's my problem.
That's right.
I'm all about a shock pot.
Yeah.
Yes.
It's like-
I'm scared I'm gonna blow my house up.
Yeah.
Yeah. One time the little thing started blowing steam.
Oh yeah, and it's like it like
I was
goes
running-
crazy.
I was running across the house.
Be my protective eyewear.
Yeah, exactly. It's a little aggressive too.
Yeah.
I like my friend's building a house and she's like asking me, and I was like, I like a good old fashioned crock pot, and she's like, you're an old lady. I'm like, I got stuff in the crock pot right now, and it is dang good. Smelling my house up.
Yes.
So it's like an air freshener and
Like I'm not gonna blow myself up.
yeah, it's like you can't mess it up either. Like there, like, you have to put it on certain pressure and do like. I don't do math outside of school. I just put a roast in this morning, threw everything in it, boom, done.
That's all gonna fall apart tonight. And then we pull it out.
It's gonna fall apart. Yeah,
Usually that's when
I know. I put it in at like 7 this morning.
Now I'm gonna go buy some. I want this now. I'm gonna go to the grocery store when I leave. Kids better be ready tomorrow.
I'm like so excited. It like makes your day, you know.
My mom used to make them like all the time. It's my favorite.
I make them with pepperoncinis.
Ooh.
Yeah, it's really good. I'll have to bring some in for you guys next time. That's like my go-to. All right, so anyways, back to work. Sorry, we were just getting a little too long. We needed a little brain break. All right, so anyways, our p-values. It was 2-tailed, so we multiplied by 2, and that will give us 0.02 and 0.05. So those were our p-value range, which that was this answer right here. So let's go plug that in. So 0.02 to 0.05. That's our p-value range. Now let's see, based off of our alpha, if we are going to reject or fail to reject, or what we're going to do. So our alpha is 0.01. I want to word it exactly like I worded it on the previous problem. Compared to our biggest or largest p-value, which is 0.05. So alpha and p, alpha 0.01, p 0.05. So that means our p is bigger. So we are going to fail to reject the null hypothesis.
That's for critical left and right.
No, that's just our answer. We're going to do the critical thing left next to me.
Oh, okay.
Going back because I want to again label it exactly the same. I like it to be like very consistent, which means that our alpha is smaller than the rejection region. So that's how we know to fail to reject. All right, so going back like we talked about to the critical value approach. To get our T critical left and our T critical right. So our area is going to be 0.05. because if we draw our little picture down here, we have two-tail test. So we know this is going to be alpha over 2, alpha 0.01. So that means it's going to be 0.005. I think I forgot a 0 there. And this will be for each tail. And then our degrees of freedom is n minus 1, so 26 minus 1, which is 25. So we can use this, so from our t table, we can find our t critical left and our t critical right.
There's a lot of process in this.
Yeah, it's just these are super long. The parents have to solve the answer twice to find everything they're looking for. All right, so degrees of freedom. We said it was 25. We're looking for the area is 0.005. So this column, going down to 25, we get 2.787. 2.787. So that means the left one's going to be negative, the right one's going to be positive. Boom, those are our two answers there. So T critical right is 2.787. T critical left is negative 2.787. And then our last step, so those were two answers, so let's box them in. And then our last step, if we know this is negative 2.787, this is positive 2.787, we need to find our rejection region. Our T observed is 2.379, which will be somewhere right here. .379. It's in the non-rejection region. It's in the white region, the non-shaded region. So that means we are going to fail to reject the null hypothesis. Since T observed is in the non-rejection region. Another one down. Another one down. Questions, comments, concerns on this one?
So this is all choice. Well, we still have to work it out. It's just going to be individual.
Yeah, like
questions.
asking, yes, yeah. Like individual
Work it
questions.
all out, and then whenever you find the answers, then you just.
Yeah, see what they want.
Okay.
Yep.
Gotcha.
Also, by the way, it'll probably be like, here's the problem, and then answer questions like 15 through
Yeah.
17, like where it'll be like you don't have to work it out once for multiple problems.
Mhm.
So that'll help. What else? Other questions? Ready for the next one?
Possibly. No.
Let's just get it over with.
Keep rolling.
What?
Keep rolling.
Keep rolling. Let's keep going. Yeah. Let's hurry up. I hear you. I'm picking up what you're putting down. All right. A random sample of 25 observations taken from a population that is normally distributed produced a mean of 58.5. Standard deviation is 7.5, so exactly the same as the previous problem. Finding the range for the p-value, the critical and observed values for the following. For t for the following test the hypothesis using alpha 0.01. This time what's different is we have our null is our mu equals 55, but this time we have our mu is greater than 55. So this is telling us that we're going to have a right-tailed test.
Kind of like it. I feel like whichever way it's pointing is which way the tail will go.
Yeah, exactly. Whatever way it's pointing is the way it's like telling you which tail it is.
I get that.
Good, yay! One thing down. All right, so let's write down what we know. We know n is 25. We know our sample mean is 58.5. We know our sample standard deviation, which is S, is 7.5. So again, our population standard deviation is unknown. So we're going to use S and T values. Meaning we're not going to go using Z. Our alpha is 0.01. Our sampling standard deviation is going to be S over the square root of n. Same thing over and over and over. So 7.5 divided by the square root of 25. Oh, sorry. 7.5 divided by the square root of 25 will give us 1.5. Our t observed. I'm trying to keep everything like where we're doing, it looks exactly the same. I don't want to go out of order so that way it's like you're getting the habit of doing exactly the same thing every time. So t observed is our x bar minus our mu all over our sampling standard deviation. So 58.5 minus our mu, which is 55, all over 1.5. Make sure to put the top in parentheses because it's the top of our fraction. So in our calculator, 58.5 minus 55 divided by 1.5. That will give us 2.333 for our t observed. Using our p-value approach, so using t observed, which is 2.333, and our degrees of freedom, which is n minus 1, which is 25 minus 1, which is 24. We are going to find the range of two areas that contain our t observed So from our t table, real quick, I'll go back to it if you're not done, but our degrees of freedom is 24. Our area that our t observed that we're looking for is 2.333. So it looks like 2.333 is between 2.0 and 2.4. So it's between these two areas of 0.01 and 0.025, going from least to greatest. So 0.01 p-value and 0.025. This time we only have a one-tailed test, so I don't need to multiply by 2. I only have a right-tailed test, so I don't need to multiply by 2.
One less step.
Yay! True. So that means we're going to take, let's go ahead and write this, 0.01 is less than our p-value, which is less than 0.025. So we're taking our alpha, which is 0.01, compared to our biggest or largest p-value, which is 0.025. So alpha and p, alpha 0.01, p is 0.025. Dang, again, p is larger. So that means we are going to fail to reject the null. Oh, scared me. Since our alpha is smaller than our rejection region. Last step, finding our critical values. Our critical value approach. We know our area, which is our alpha, is 0.01. There's only one, so I don't have to divide by 2 or anything. Our degrees of freedom is n minus 1, which is 25 minus 1, which is 24. So from our t-table, our t-critical (24) degrees of freedom column, looking at 0.01, that means 2.492. Now looking at our graph, in the middle we have 0. It's a right tail test, so we know it's going to be positive. Last but not least, our t observed is 2.333, which will be somewhere over here. So we are going to fail to reject the null hypothesis since our t observed is in the non-rejection region. Another one down.
Another one
Bites dust. Don't laugh at me. All right. Questions, comments, concerns? How can I help you with this one?
I'm
Yeah.
interested at the top.
Yeah. Is that enough?
What does that say at the very top right?
This?
It says,
So use S and T. That isn't what it is. Sorry, that doesn't look like it answered well. Good to go? All right, let's keep going. Next example, according to an estimate, the average debt for college graduates is $34,400 in 2010 to 2011. A random, sample of 485 showed this year's average debt is $38,000 with a standard deviation of 5,360. Does the data provide significant evidence at a 5% significance level to conclude the current average is higher than 34,400? Use the p-value and critical value approaches to make a conclusion, and we're going to use our t-table. All right, so let's get started. Let's start by writing down what we know. So just like before, we know our n value is 485. Our this will be our mu. So mu is 34,400. Our x bar, sample mean, is 38,000. Standard deviation, they give us the sample standard deviation, which is S. So just like before, our population standard deviation is unknown. So we're going to use S and T values, which is 5,360. And we know our alpha, or significance level, is 0.05. This time we have to write our own hypotheses. So our null hypothesis and our alternative hypothesis. We're saying that the current average is higher than 34,000. So boom, right here, that's our alternative hypothesis. So our mu is greater than 34,400, which will tell us it's going to be right tail test. And that means our null is that mu equals 34,400. So we need to find our sampling standard deviation, which is S over the square root of n, which is 5,360 over the square root of 485. Oh no. So in our calculator, the sampling standard deviation should be 243.385. So that means our t observed is our x bar minus our mean all over our sampling standard deviation. So 38,000 minus 34,400 all over 243.385. Make sure to put the top of your fraction in parentheses. And that will give us our t observed is 14.791. So I'm going to circle that because that's one thing that we're going to need. Or box it in or whatever. So going to our p-value approaches, the same thing like we've been doing this whole time. We are going to use t observed, which is 14.791, and our degrees of freedom, which is n minus 1, which is 485 minus 1, which is 484, to find the range of the two areas that contain t observed. So from our t table, couple different things here. So 485 for our degrees of freedom's too big for our thing, so we're going to use infinity. So this is too big for our t table. So we're going to use infinity. So that's the first thing. And looking for our t observed, which is 4.791. So going down here looking for 14.791, it's too big than all of these things. So a couple of different things here. So that means it's going to have to be, whatever it is, it's going to have to be bigger than this biggest one. So bigger than this. So bigger than 0.001. So our p-value has to be larger than 0.001. I'm sorry, smaller than 0.001. Or, by the way, if you have to write a range, the smallest it could be is 0. It can't be a negative p-value because the p-value is our area. So it could be between 0 and 0.001. Yeah, was there a question? No. So that means using our p-value approach, we're going to take our alpha, which is 0.005. By the way, it's only one tailed, so don't multiply by 2. Compared to our largest p-value, which is 0.001. This time, our alpha is bigger, so that means we are going to reject the null hypothesis. Our alpha is this time larger than the rejection region. And then lastly, our critical value approach. Our area, which is our alpha, is 0.005. Our degrees of freedom is n minus 1, which is 485, minus 1, which is 484, which we know in our table is going to be infinity. So from our table, we know that our T critical is going to be looking at our last infinity row, looking at alpha 0.05. So we get 1.645. It's a right-tailed test, so I know it's going to be positive. So looking at our little drawing, I don't know what happened. I just dropped the ball on all our graphs. Sorry. So our right-tailed test, we know this is 1.645. Our T observed was 14. Dang it. Thank you. Up. That was weird. Okay. So if our T critical value is 1.645, going to our table, looking at infinity because it was going to be larger than 75, and looking at the column when our area is 0.05, we found that our T critical value was 1.645. It's a right-tailed test, so we know it's positive. Our T observed is 14.791, so it's going to be somewhere way over here. So it is in the shaded region, it is in the rejection region, so we are going to reject the null.
Where did you get, okay. How'd you 1.645?
So going to our T table,
Right.
our area is 0.005.
2.576.
So this is to fill out and give back to you?
That's for you to study guide to fill out and get back to me for next week for the test, yeah.
Alright, so if I find the previous ones and do them, give those to you as well?
Yes, they're on Blackboard.
Wait, you might want to take a look at one of your computers.
Okay, thank you. What? I'm sorry.
The area is 0.
Oh, I'm sorry,
0.005.
I'm sorry, I added a
Okay,
0.
because I've been kind of wondering that you've been writing 0.005 the whole way through,
And then all of a sudden I changed.
No, you wrote it early on the
Yes, I did,
value
right here.
Because I was trying to be like, okay, where does 0.05?
I'm sorry, you're right.
Because it was 5% and you made it 0.05.
Yes.
Okay.
Okay, yeah, so but that's still bigger, so that's good. Thank you for noticing that.
I wanted to stop a long time ago, but I thought I was wrong.
No, you're good, you're good. So that's 0.05. Dang, I even did it right on here. So 0.05 and infinity. That's 1.645.
Yeah, that's
Bingo.
why I was like, okay, maybe she did write too many zeros.
I don't know. Yeah, I did write too many zeros. But I read it right. I don't know. My brain's
Maybe I
weird.
was listening to what you were saying. I don't know.
Thank you for catching that. So it's in the shaded region, so reject the null hypothesis. Since T observed is in the rejection region. Other questions, comments, concerns on this one? So next we have one that's a little bit different. We have proportions. trying to go through. Are you ready for the next one? All right, so according to New York Times, in a CBS News poll conducted during June 24th, June 28th, 2011, 55% of the Americans, so boom, right there, 55% knows or tells me it's going to be proportions, which means we're doing like with like p-values and q's and all that good stuff. Of the American adults polled said that owning a home is a very important part of the American dream. Suppose this result was true for the population of all American adults in 2011. In a recent poll of 2,000 American adults, 62% said that owning a home was a very important part of the American dream. Perform the hypothesis test to determine whether it's reasonable to conduct the percentage of all American adults who currently hold this opinion is higher than 55%. Use 10% significance level and both the p-value and critical value approaches. Round our answer to 2 decimal places and the p-value to 4 decimal places. Okay, let's start. So let's see what they gave us. They gave us our p-value, which is like our mu, of 55%, which is 0.55. They told us n is 2,000. They told us our population proportion, so our p hat is 62%, which is 0.62. And they told us our alpha is 10%, which is 0.10. Looking at this, we can find our Q, which is 1 minus P. 1 minus 0.55, which is 0.45. And it says that hold this opinion is higher than 55%. That is our alternative hypothesis. That our p-value is higher than 0.55. And then our null hypothesis is that p equals 0.55. So boom, dang, again, a right tail test. So let's find our sampling standard deviation, which remember going back is the square root of p times q over n. So the square root of 0.55 times 0.45 all over 2,000. Which is 0.0111. That means our z observed is going to be our p hat minus our p all over that sampling standard deviation. So our p hat was 0.62 minus 0.55 all over that 0.0111. Remember to make sure that the top of our fraction goes in parentheses. And that will give us 6.31. It says round z to 2 decimal places. So z observed is 6.31. And it's going to be like the same thing we've been doing. Just this was our only little change so far. Our standard deviation. So going to our p-value approach. We are going to find the area, which is our p-value. Before we looked at the t-table, we're not doing t's this time. So now we're looking for, we can put this into our calculator. Go into our normal CDF. So let's do a little graph to see our upper and lower boundaries. So right tail test. If this is our 6.31. So our lower bound is 6.31. Our upper boundary is infinity. So 1e to the 99th. Z value, so 0 and 1. So in our calculator, second bars, normal CDF, lower boundary 6.31, upper boundaries infinity, 0 and 1, which will give us 1.401 e to the negative 10th, which is just scientific notation, 1.401 times 10 to the negative 10th, which means move our decimal 10 times to the left, which is pretty much 0. So our p-value is going to be 0. Just like we did earlier, we can take in our alpha, which is 0.10, compared to our p-value, which is 0. So alpha 0.10, p is 0. Our alpha is going to be larger, so that means we are going to reject the null. Hypothesis. Since our alpha is larger than the rejection region. And then last but not least, our critical value approach. So we need to find our z critical this time, which we can do in our calculator. As our inverse norm. Let me draw a quick picture because I need to find my area to the left. So if this is 0, we know our alpha is, it's a right tail test for one. We know this alpha is 0.10. In my calculator, I need to put the area to the right. So this area to the right is 1 minus 0.10, which is 0.90. Ew, something on my nail. Disgusting. So 0.90 is our area to the left, comma 0, comma 1. Second bars, going down to inverse norm. Area to the left is 0.90, so that way it's the same for everyone. Boom, there's our critical value, 1.28. So if this is going to be 1.28, our z observed was 6.31, which is like way over here. So it's in the shaded region, it's in the rejection region. So we're going to reject the null hypothesis. Since z observed is in rejection region. And that's that example. We're going to do one more next. That's going back to proportions again. So we can see another one of these. The next one's going to be a two-tailed test, so that way we can see that worked out. By the way, before we go there, because we rejected the null hypothesis, we said that it's not equal to 0.55. That means we accepted the alternative hypothesis, so we can conclude that the percentage of all adult Americans who currently hold this opinion is greater than 55%. We rejected the null hypothesis, so that means we have to accept the alternative. So it's greater than. Questions on this one before we go to the next one? Next one, page 14. According to a Pew Research Center nationwide telephone service of results conducted between March 15th and April 24th, 2011, 55% of college graduates said that college education prepared them for a job. Suppose this result was true of all college graduates at that time. In the recent sample of 1850 college graduates, 59% said that college education prepared them for a job. Is there significant evidence at a 2% significance level to conclude that current percentage of all college graduates who will say that a college education prepared them for a job is different from 55%? Use both P and Z, all of that good stuff. Okay, so let's start here. So it's 55%, so boom, I know it's proportions that we're dealing with. And that's going to be our p-value, which is 0.55. While we're here, we know we have to find q, so let's go ahead and find q, which is 1 minus p. So 1 minus 0.55, which is 0.45. Our n is 1850. Our p hat, our sample proportion is going to be 59%, which is 0.59. 2% significance level, so our alpha is 2%, which is 0.02. It says is different from 55%, so this is our alternative hypothesis. Is different from means that our p-value is not equal to 0.55. That's going to tell us it's a two-tailed test. Our p-value is equal to 0.55 will be our null hypothesis. Just like we did earlier, we need to find our sampling standard deviation, which is the square root of p times q over n. So the square root of 0.55 times 0.45 all over 1850. Which will give us 0.0115. 66, which will round to 0.01157. can use this to find our z observed, which is p hat minus p all over the sampling standard deviation. So 0.59 minus 0.55 all over this 0.01157. Make sure to put the top of the fraction in parentheses. .01157. So our z observed will be 3.457, which will be 3.46. We can now find our p-value approach. Which means find the area, which is our p-value. So just like we did on previous tests, our area in our calculator is going to be the normal CDF. I need to do my left bound, right bound, all that good stuff, so let's draw a quick graph. We know it's going to be a two-tailed test. We know this is 3.46, so that means this has to be negative 3.46. So if I find one of them, I can multiply it by 2 to find all of the area. So let's use this one. So our lower limit's going to be negative infinity. So negative 1 e to the 99th. Our upper boundary is going to be negative 3.46. Mean is 0, standard deviation is 1. So in our calculator, second bars, normal CDF, lower limits negative infinity, upper limits negative 3.46. And we get 2.701 e to the negative 4th, which is 2.701 times 10 to the negative 4th, which means move our decimal 1, 2, 3, 4 times to the left, which is 0.0002701. It says round p-value to 4 decimal places. So 1, 2, 3, and then 27 will round up to 3. Remember, we have 2 areas, so that means we need to multiply by 2. Since it's a two-tailed test. So our p-value is going to be 0.0006. Now taking our alpha, which is 0.02, compared to our p-value, which is 0.0006. Our alpha is bigger, so that means we are going to reject the null. Our alpha is larger than the rejection region. Last but not least, our critical value approach. We have our little graph. We know it's a two-tailed test. We know our area, because it's 2, is alpha over 2. Alpha 0.02. So each tail is going to be 0.01. So our Z critical is going to be the inverse norm in our calculator. Our area to the left is 0.01. Comma 0, comma 1. So second bars, inverse norm, area to the left is 0.01. And we get negative 2.33. So this one's going to be negative 2.33. This one's going to be positive 2.33. So negative 2.33, positive 2.33. Last but not least, our Z observed is 3.46, which is somewhere over here. Which is in that shaded region. So we are going to reject the null. It's in the rejection region. Oh, last step, we need to fill out this. So it says, can we conclude the current job percentage of all college graduates who will say that college education will prepare them for the job is, we rejected the null. So that means we said the null was not true, so we took over the alternative. So that means is not equals to, so is different from. That's the wording they used. So it's different from, which means not equal to. So because we rejected the null hypothesis, that means that we accepted the alternative.
Bye.
Bye, thank you. Questions, comments, concerns on this one? Good to go?
That's a good question.
I think it's 25 questions.
The
Well, just from chapters 8 and 9. So a little bit of chapter 8, then do a little bit of chapter 9.
a little bit of chapter 9. Wait, Jesus.
I know, my hand is killing me.
I know mine too.
All right.
I do this all the time.
That's why I have like baby hands with huge knuckles. All right, let's knock these out. We're so close, so close. This is the last thing forever for stats. So we can do this. We can do it. So in a random sample of 550 observations, produce a sample proportion equal to 0.3. I like this one. It's to the point. Find the critical and observed values of Z for the following hypothesis test using alpha 0.025. It even gave us the hypothesis test. P is 0.30. The alternative is that P is greater than 0.30. So let's write down what we know. So we know our N value is 550. I can't even write. 550. Sample proportion, so that's telling us our p hat is 0.38. Our alpha is 0.025. This is telling us our p-value is 0.30. So that means our q value is 1 minus p, so 1 minus 0.30, which is 0.70. By the way, this is telling us that it's going to be a right-tailed test. They didn't ask us for our p-values, so I only have to do the critical value approach this time. Even better. Even better. All right, so let's roll through this. Our sampling standard deviation we know is the square root of p times q over n for our proportions. So the square root of 0.30 times 0.70 all over 550. So the square root of 0.30 times 0.70 divided by 550, which will give us 0.01954. So we can use this to find our z observed, which is p hat minus p all over our sampling standard deviation. P hat was 0.38 minus p from our hypotheses is 0.30 all over that sampling standard deviation, which we just found. Make sure to put the top of the fraction in parentheses. So 0.38 minus 0.30 divided by 0.01954. And we get, rounded 2 decimal places, 4.09. So our z observed is 4.09. Now just to find our z critical, we don't have to do our p-value approach. Let's draw real quick. We know it's a right-tailed test. We know this area is alpha, which is 0.025. In our calculator, we need to put the area to the left, which is 1 minus 0.025, which is 0.975. So in our calculator, we can do the inverse norm. Our area to the left is 0.975. Comma 0, comma 1. Second bars, inverse norm, 0.975 is our area to the left. Mu is 0, standard deviation is 1. So that means our z critical is 1.959, which is 1.96. So if we know this is 1.96 and we know our z observed is 409, somewhere over here, it's in the shaded region, it's in the rejection region. So reject the null. Since z observed is in the rejection region. We are getting closer. Questions, comments, concerns? How can I help you with this one? 3 more. You can do it. You can do it. 3 more. All right, 16. Consider, again, short, sweet, to the point. We got this. Our null hypothesis is P is equal to 0.70 versus our alternative is P is not equal to 0.70. So boom, we know it's a two-tailed test. A random sample of 600, so N is 600. Observations produce a sample proportion, so that's our P hat, is equal to 0.68. Using our alpha is 0.01. Would you reject the null? Yes or no? So I can choose whether I want critical value or p-value approach. We just did the critical value approach, so let's do the p-value approach. But it doesn't matter. Either way, you're still going to get the same answer. So choose either p-value approach or critical value approach. Let's see, before we even do anything, we know that we're going to need our sampling standard deviation, square root of PQ over N. We know that P is 0.70, so that means Q is 1 minus P, so 1 minus 0.70, which is 0.30. So the square root of 0.70 times 0.30 all over 600. Square root 0.70 times 0.30 over 600. 0.01871. So we can find Z observed, which is P hat minus P all over the sampling standard deviation. P hat is 0.68 minus P is 0.70 all over that sampling standard deviation, which we just found. Make sure to put the top of the parentheses in, top of the fraction in parentheses. So 0.68 minus 0.70 divided by 0.01871. And we get our Z observed is negative 1.068, which is negative 1.07. So let's use our p-value approach. We know it's going to be a two-tailed test. So our p-value, which is our area, is in our calculator. Our normal CDF. By the way, our Z observed was negative 1.07. and then positive 1.07 for the right side. So let's use this left one is going to negative infinity. So negative 1 e to the 99th for our lower boundary. Our upper boundary is negative 1.07, comma 0, comma 1. Second bars, normal CDF, lower boundary is negative infinity, upper boundary is negative 1.07, comma 0, comma 1. Boom, that will give us our p-value is 0.1423. But remember, there's two of them. So that's saying that this area is 0.1423. So that means this area is 0.1423. So that means there's two of them, so we need to multiply by 2. So our p-value is that number times 2, which is 0.2846. So now we need to take our alpha, which is 0.01, compared to our p-value, which is 0.2846, alpha, p. Oh, sorry, thanks. P is bigger, so failed to reject. The null hypothesis our alpha is smaller than the rejection region. So remember, the question from the get-go was, would you reject the null hypothesis? No, because we failed to reject it. Last page, last page, last page. Questions on 16. You can do it. You can do it. Last two. Page 17. A random sample of 480 observations. So let's go ahead and write down everything while we're reading it. So n is 480. Produce a sample proportion. So p hat is going to equal to 0.37. Find the critical and observed values for z for the following test hypothesis using alpha 0.1. We know our p-value is 0.30, so that means our q is 1 minus our p, so 1 minus 0.30, which is 0.70. By our alternative hypothesis, it's that it's not equals to, so we know it's going to be a two-tailed test. It's just looking for critical and z values. We only have to use the critical approach here. We don't have to use the p-value approach, so that's good. So our sampling standard deviation is the square root of p times q over n. So the square root of 0.30 times 0.70 all over 480. Which will give you 0.0209. So we can find our z observed is p hat minus p all over our sampling standard deviation. So 0.37 minus 0.30 all over that 0.0209. Make sure to put the top of your fraction in parentheses. And we get our z observed is 3.349, which is 3.35. So we just need our critical value, so we can just use our critical value approach. It's two-tailed. We know this is alpha. There's two of them, so alpha over 2, 0.1 over 2, which is 0.05. Same thing over here. So to find our z critical in our calculator, we can find the inverse norm. Our area to the left is 0.05. On the 0, 1. Second bars, inverse norm, area to the left is 0.0501. And we get negative 1.64. So that means I know this left one is negative 1.64, this right one's positive 1.64. So z critical left is negative 1.64, z critical right is positive 1.64. Last but not least, z observed is 3.35, which is somewhere over here. Which is in the shaded region, so we are going to reject the null. And guess what? We made it to our very last example of the final class. Dun, dun, dun.
It's 2 points.
And it's what?
47 hertz, really.
That's kind of all of it. You ready? We can do it. Our little fingers can do it. All right, so last one. According to the study, 11% of children in the U.S. live with at least one grandparent in 2019. So boom, automatically I know its proportions. So I know my p-value is 11%, which is 0.11. So while we're here, I know q is 1 minus p, so 1 minus 0.11, which is 0.89. Suppose that in a recent sample of 1580, so our n value is 1,580, 238 were found to be living with at least one grandparent. Okay, so they're kind of trying to trick you here. So our p hat is saying that 238 out of our total 1580. So plugging that into our calculator, 238 out of our total 1580 is going to be 0.1506. at a 2% significance level, so our alpha is 2%, so 0.02. Can you conclude the proportion of all U.S. all children in the U.S. who currently live with at least one parent is higher than 11%? So boom, that's our alternative hypothesis. So our proportion is higher than is larger than 11%, so 0.11. And that means our null is that our p equals 0.11. Use both p-value and critical value approaches and then form a conclusion. So looking at this, we know it's going to be a right tail test. We know we need to find our our sampling distribution standard deviation, which is the square root of p times q over n. So the square root of 0.11 times 0.89 all over 1580. Square root 0.11 times 0.89 divided by 1580. That will give us 0.00787. Finding our z observed. We have p hat minus p all over that sampling standard deviation. So we have 0.1506 minus 0.11 all over 0.00787. Make sure to put the top of the fraction in parentheses. 0.1506 minus 0.11 divided by 0.00787, which will give us a z observed of 5.16. Using this for our p-value approach. Our p-value, which is our area, is if we put this into a little graph, we know we have a right tail test. We know this is 5.16. So in our calculator, we have our normal CDF. Lower boundary is 5.16. Upper boundary is infinity, which is 1 e to the 99th. On the 0, 1. So second bars, normal CDF. Lower limit is 5.16. Upper limit is 1 e to the 99th, 0 and 1. We get 1.237 e to the negative 7th, which is 1.237 times 10 to the negative 7th. Moving our decimal 7 times to the left, that's pretty much about 0. So our p-value is going to be 0. So we can take our alpha, which is 0.02, and compare it to our p-value, which is 0. Alpha is going to be bigger. So that means we're going to reject the null. That's our conclusion. Because our alpha is larger than the rejection region. Last but not least, critical value approach. Quick little drawing. Right tail. We know this is alpha. One tail, so just 0.02. So that means our Z critical is going to be in our calculator. Our inverse norm. Our area to the left is 1 minus 0.02, which is 0.98. Comma 0, comma 1. Second bars, inverse norm, 0.98, 0, 1, area to the left. 2.05. So that means this number right here, this value is 2.05. Our Z observed is 5.16, so it's going to be somewhere over here. So that's in the shaded region. So that means we are going to reject the null.
We can use either of those approaches.
Yes, but this one told us to use both p-value and critical value. But yeah, you get the same answer.
I feel like it's more clear for me when I use the critical value.
Me too, to be honest. But yeah, I agree. I like the critical value better. It's a little more straightforward, maybe. But yeah, either one give us the answer. So if it like the previous ones didn't really say, so you kind of do whatever. Reject the null since our Z observed is in rejection region. Note, there will be questions that give N and P and then ask if the sample size is large enough. So just remember that for those questions, N times P has to be greater than 5 and N times Q has to be greater than 5. It was something that we did earlier. I just wanted to kind of, as I was going through all the examples, I wanted you just to remember that. And we did it, guys. Congrats. That's all of Chapter 9 notes.